Good evening, everyone. Thank you again for coming today. And it's actually my pleasure to be chatting with you, Professor Shadi. And I think what we've heard now hits every one of us. So thanks again. First, I want to ask you to tell us more about yourself, your family, your interests, and maybe your background growing up in Lebanon.
Yes, thank you so much. It's my great honor actually to be here, honored by the presence of everyone of you. I've had many friends actually since my school times, and I've had also some of my colleagues here, and a lot of people who were my colleagues on LebNet a couple of years back when I started volunteering to this amazing community. I take pride in what we accomplished together, but I'm very proud of how you carried on after I lowered my participation. So congratulations to you. I was born in Lebanon, in a little town on the foothills of the Barouk mountain. It's called Kifraya. We are a small town of about 100 homes. If we look east, we see the Bekaa Valley extending for about 4 miles in this spot between us and the next town on the other side. So this is the view that I had when I grew up looking into the Bekaa Valley. Growing up, I attended a German missionary school. It's Johanna Ludwig Schneller Schule. This is a boarding school that cared for orphans throughout Lebanon and for some of the children from nearby towns where I was living. In Schneller, we of course hailed from every corner of Lebanon. We sang the Lebanese anthem every morning, and we attended church during the day, and some of us went to the mosque in the afternoon. So schools like Schneller, which I know some of you support, help build character, civility, rigorous academic training, and provide opportunities for someone like me to change or overcome their circumstances and make better versions of themselves. So what you do and what we heard from Jenny to support children in Lebanon, especially those who go to school at this age, is extremely important. So attending Schneller in the early formative years for me was critical to who I became, and it taught me how to become a human and also a citizen. So, growing up, since the time I opened my eyes to life, I had a very loving mother with incredible patience, who I still fly on her wings until today, as I do in this picture right here. Throughout elementary and middle school, we woke up together every day between 4 and 5 a.m. to recite the classes before school. That starts at 8, and we study till late at night. So I was, in a sense, my parents' hope in a family of 4 to get an education, to earn a better living. I loved cars since I was very young, and I also loved physics. However, in 5th grade, I was 5th in my class, which was not enough for my parents. So it was decided at that point that I should go and learn how to be a car mechanic, because my chances are going to be low to succeed in academia. I didn't know that was actually for my greatest fortune. It's a true story. So in the 6 consecutive years, I learned in the summer the practice of making car repairs. And when I took physics later, it came natural to me because I started doing it and experimenting with my hands at a very early age. And then later in my life, I was never overwhelmed with experimental tasks in my career. And then came the 1990s, and the economic situation was not very good throughout Lebanon, and the mechanic shop had to be closed. So I started working in the summers in the vineyards in our town. We had 2 of them. They're still up till now, doing various labor jobs to support my high school and college tuition. And when the vineyard season was not active, I took jobs in assisting for providing electricity in buildings with my uncle, or even manning a pistachio stand on the main highway for 2 summers in the Bekaa Valley. In these various jobs, I learned the humility of human nature, and I connected to the soil in Lebanon. I still feel, up to this day, the grains of the sands on my cheek as we rested in between shifts when we were working in the vineyards. And I spoke before in a LebNet event about the fog carrying the wine in the valley. So this is the fog in the valley covering all the vineyards. And we used to rise before sunset so that we can go and do our shifts before it gets hot. And walking down, you can smell the smell of the wine with the fog coming from the winery and spreading throughout the whole valley. And so I learned at an early age to do the job no matter what the job was, and to do it to the best of my ability, and to finish the job. Every fall, when we harvest olives, 3 generations of my family sit around a large pile of olives that look like this to remove the leaves and prepare them for pressing for olive oil. And this is to be able to consume it through the year. We have a small amount that is enough for us and for my uncle's family. And today, we had some of that olive oil that came from my parents' olives that was outside. If you haven't tasted it, please do so after the event. So when this first came and I opened and I smelled the olive oil, immediately flashes of pictures of my family came to my mind and to my grandmother. So I connect through it to all of my family who are in Lebanon or in heaven. So that's the story of me growing up.
Thank you so much for telling us about your childhood. And now can you tell us more about your education path leading to professor, and if you always wanted to become in academia?
I think maybe my parents were right, because I'm not able to use PowerPoint very well.
But you are able to do other stuff.
Right. So you probably want to exit from PowerPoint and come back to it again. So after I finished college, I went to the Lebanese University in the Hadath, what we refer to as Kulir Al-Ulum. And it was a single building. Now it's a university town. And there I majored in physics, and I focused on electronics in the last 2 years. And in the Lebanese University, most of the students graduate and go to France in order to get their master's or PhD. We had no experience in people coming to the US. Even Rami, who went and was 2 years above me in the same university, went first to France and then came here, and we met in San Diego. So I had a lot to research and learn, and I applied to graduate schools through gradschools.com. There was no precedent for me. And somehow I got an offer from a university in Texas called Southern Methodist University. I don't know if I realized at the time, what Methodist meant, or even if it would have mattered to me. It was just an admission. So I came, yes, with very little and with very big determination. And I was not funded for the first semester, and then I did well, like we do when we come from abroad and we want to try our best. And then I started to get my foot into the system and be supported in the system as I do well. So that was the Lebanese University right there. Yes, it was on the screen before. And this is SMU. At SMU, I started doing research on flexible sensors. These are thermometers for infrared sensing, or also for temperature sensing. And we were implementing them on flexible substrates. Funding around that time was for military applications, to make gloves in dangerous areas, or to make night vision, and also to put on curved surfaces of airplanes. I didn't know why they wanted to do that, but we had to do the flexible sensors. And these were really good record performing sensors. In 2003, I came to UCSD, and here I thought I learned how to do sensors, so I should learn how to do circuits. And if I combine them, I might do something unique in the future. But the plan didn't go that way. I had to go back and do semiconductor devices at the time, and it led me to where I am today. So I picked up 2 slides from my PhD thesis defense. Around that time, between 2003 to 2008, those who know about silicon CMOS technology, we were at 90 nanometer node and trying to predict, what type of transistor architecture or material will allow us to keep shrinking computers or processors and making them faster and cheaper. And so one approach was to stack the transistors vertically so that we can put multiple cells per unit area if we do that vertically. And the one-dimensional structures were proposed, and I worked on this area. I tried to understand the materials properties of these vertical structures, to understand their electronic properties, and to make high-performing transistors from that. And I only did that. I don't think I did anything else except participating in some parties with the colleagues that we have here from back at the time. For about 3 years, no results came out, and then results started to come, published 7 papers in 1 year, and got many awards. And those are my advisors here at the bottom. So I was contributing to the fundamental science of how to control the material property and morphology of these structures. And then in 2008, I went to Los Alamos National Lab, and these are slides from my interview back at UCSD summarizing what I did in Los Alamos. I had met a few years earlier Tom Pickrell, who became my PhD advisor, and he was a very solid material science person, very focused in a specific field, and understood that I'm also very focused, so he gave me an opportunity at Los Alamos. And he told me, come and let's build a program together. This was actually his second career. He has retired from Los Alamos, from San Diego National Lab before going to Los Alamos. So we built a program. We hired over half a dozen postdocs and more students. Many of them now are faculty in different places in the world and in the US. And the work there was focused again on material science and electronics. Tom was a champion for me at Los Alamos, and I was really very focused, putting 14, 16 hours a day like I did in my PhD. So I became an Oppenheimer Fellow there in 2010, and that was a very proud moment for me because I was the first from the Arab world to get that honor. And that actually helped me, boosted my confidence to go to the next steps in my career. I also got a number of other awards. So how, is this background that started from wine and then, material science ended up in brain interfaces? Around 2008, I picked up a book from the bookshelf of one of my classmates, and it's Liars, Lovers, and Heroes, and it talks about how brain science tells us about who we are, written by Terry Sinowski. And for about 7 years, I was just, my work was very small, so I looked into brain science, thought it's very, very interesting, and I started to become curious about this field. And then around the same time in the fall, a little bit later, I went to a conference where they talked about emerging technologies in electronics. And they showed 2 different types of interfaces to the brain. And some of the structures that I was working on are similar, but could merge the advantages of what's used in brain interfaces. So I went back to my postdoc advisor in Los Alamos, and I asked him, could we work on this area? And he supported me, and we got a grant a couple of years later, and then I moved to UCSD. And then in UCSD, it's a story where the research has emerged. So that's my path to the academic position. I wanted to become a professor so that I can go back to Lebanon and teach and help other people like how I was helped. But then I enjoyed the research that I was doing and took the research trajectory.
Thank you. And you mentioned the work on the brain. So can you tell us more about it and what problems are you trying to solve?
Definitely, definitely. So I was doing one-dimensional structures, started in Los Alamos, studying how individual cells basically send signals. And this is important for discovering how ion channels work and to be able to treat neurological diseases if we are able to look at the small potentials during cellular activity or neuronal activity and how that is modulated by drugs. Then we can use this for drug screening. That was the goal. But then when I joined UCSD in 2013, the Brain Initiative started, and UCSD folks were heavily involved in the Brain Initiative. And that's Terry, who we saw in the previous slide, who wrote that book that got me a little bit excited. So Terry and colleagues arranged for meetings between engineers and clinicians at UCSD. So there I met my colleague Eric Hallegren, who saw me presenting about these one-dimensional structures, and he told me, if you make them a little bit longer, I'll use them in humans. And that's how we started making now devices to be used in humans. So I'll tell you a little bit about the journey to use our devices in humans, where we were approved for a clinical trial earlier this year. We use those devices for a number of applications. One, during surgery, and that's to map eloquent regions in the brain, that is, regions that are used for memory, for language, and for motor function. And the surgeon, and we have one of them here, Dr. Benheim, that's to help guide where the surgery is done. So this is done during surgery. Can we go to the next slide? So the other application is to look for the origin of epileptic seizures, and sometimes those cannot be discovered with non-invasive imaging. We have to go into the brain and measure where is the origin of the seizure. And when it's a very cloudy picture of where the seizure is, patients need to be implanted with electrodes for several days. And thanks. It's good. And they're monitored with this. So this is for epilepsy patients, and then for other types of neurologic diseases that need modulation with electrical charges over their lifetime, that's a field called neuromodulation, and that's used for movement disorders, also for epilepsy if resection wasn't needed, and then for obsessive compulsive disorders. And there are clinical trials to treat depression and chronic pain with these devices. Next slide. Also, brain-computer interfaces is an emerging field. But this is what's used today. Those are the devices that rest on the surface of the brain during surgery. They hardly sample the brain activity well. They undersample it because the separation is about 1 centimeter between the contacts. So you miss a lot of the critical regions that you need to understand what's happening there. So basically the picture of the brain that we see today with today's technology is similar to the picture of Jupiter with one of the ancient telescopes that we have here. What we want to do is have a high-resolution telescope but for the brain, so that we can see the small changes on the local level, but also see the big picture. So we want that high definition to be over a wide area so that we don't miss how the brain formulates our actions and how disease is formed in the brain. So this is one of the devices that we use during the surgeries. It's very thin, leverages technologies that are used in display screens, so the same manufacturing technique is used to make this type of device. And the breakthrough was in the sensing material that allowed us to make these contacts very small and not compromise their sensitivity. Next slide. So in 2019, we started using those in humans. We put hardware during their surgery. Some patients are awake. We put hardware to monitor their behavior. Here we were tracking the hand motion, and we were recording from the surface of the brain activity. And with the resolution that we have, we now can look at brain waves, the interaction between motor and sensory regions in what we are seeing right here. This is a two-dimensional representation of the activity in the brain during movement. The background are electrical potentials, and the arrows are basically the phase. So this is how waves go back and forth between the motor and sensory region when a hand is being closed. And we are sampling that at very high rates, so we see the phase precesses in some of the frames in this video. These are my colleagues who I started working with them 2015 with Dr. Dayeh, and we went through many iterations. I'll show you some a little bit later on the slides. And Dr. Raslan, who is in Oregon, we started working together in 2019. And
sorry, I thought you were done.
that's good. We can go. This is showing basically epileptic discharges on a patient that had a tumor that's seizing or having epileptic discharges. So we can monitor where the discharges start and how they spread. And we can interrogate that either by surgical decisions or by delivering charges locally in order to prevent these seizures from spreading on the brain. Let's go to the next slide, please. I have one technical slide, and then we can then talk about people once more. So earlier this year, we published a paper in which now we project that activity directly from the surface of the brain. So this is like a thin, flexible cell phone placed on the brain. When the surgeon is doing the surgery, they don't need to talk to somebody across the room and understand where's the healthy tissue and where's the diseased tissue. We can project that to them directly from the surgical field, showing that the green, for example, is healthy and the red is bad, so that they can avoid doing anything to the green and do the resection in the red. Let's move to the next slide, please. 2021, we got funding from the NIH to move to the next stage of monitoring brain activity for longer time, for up to 30 days, not only during surgery. So what we're doing right now is a wireless epilepsy monitoring system. This includes the technology that interfaces with the brain, the electronics that's housed within a titanium can, and then antennas for data and power delivery. All of this will be implanted in the patient. The skin will be closed, and then on the other side, we have a mating antenna and a single wire that goes to a cell phone to transmit the data by Wi-Fi. And this is for 4,000 channels, sampled at 2 to 20 kilohertz. So it can be up to 3 gigabits per second, the amount of data that comes out. There are engineering challenges at every aspect of this technology. And then if we want to penetrate the brain, like the MRI image that we saw, we have a new device also that allows us to do this. This picture. This is Dr. Dayeh demonstrating that the size is too big. We need to make it small. This was actually the very first prototype. So usually she does that on my head, and my head is, is long, so it would fit. So eventually I brought her a normal head, my postdoc student, and she told me it's still a little bit large. So we're going to, actually the size that we have right now is 40%. That was a prototype to show that the engineering works. And the next step is to do the one that will go to the FDA for the clearance. And on the previous picture, so this is with Sharon and Ayman, and Ayman is one of the top neuroscientists in the spinal cord. So what we're doing in the brain, we'll start doing in the spinal cord over the next few years. So why is this important? Today, when patients are kept in the epilepsy room, this is how the setup looks like. You have a lot of wires that are coming out from the head of the patient. They can't change their clothes. If they need to go to the bathroom, it would be a very big job. This is heavy, it can cause infection, so they discharge them at an early time, even before a medical conclusion has been reached. And this is also a wired system, and it's manually wired. They have to plug in every wire one by one. Next slide. So the impact, what we are doing is that we'll eliminate all of this. It will be wireless, people can move around, they can even shower. And what we really are after is ambulatory monitoring. That is, people can come have the surgery, be implanted, go home, be observed in their naturalistic environment, not within the hospital environment. And this allows us to democratize basically patient care and have more people have the opportunity to be treated with this technology. Let's go next slide. So you can keep clicking here. And in the next two slides, I'll tell you the story that this didn't come overnight. It has been accumulated over years. Some of the wording is not showing up here, but 2015, we were at about 64 channels, and then, it's all right, and this is when we started working with Halger, and then 2019, 2020, we went to 2,000 channels, 2022, we started working in 4,000 channels, and now we slowed down so that we can keep it in the brain for longer durations of time. And now we figured out a way to go to 100,000 channels, and that would be a brain telescope. And soon we'll start implementing this. Now, next slide, please. Now, this shows the funding as a function of here. And this one, there are some arrows, so please, and stop there. So I started work in this area around 2012. It took about 7 years for the NIH to kind of appreciate what I'm doing. I got my first grant in 2019 from the NIH. And then around this time, actually, before 2019, yeah, I was thinking if I was in the right job because I have been trying really hard, and this is a long time. And then I heard the pastor saying, you should be happy for other people succeeding because your time will come. So I waited for my time to come. And then, next year my time came. It was the last year in which I can apply for this NIH Innovator Award, and it happened. And then a year or two later, we got a large grant for this epilepsy monitoring. And so maybe other stories that the path of success is linearly increasing, but there's a lot of stagnant time, and it comes in jumps, and you never know when that jump will come. And so that's the brain work.
Brain part. Yeah,
Yes.
thank you so much. That's very interesting.
And there are a lot of people who, I'm not acknowledging one by one, but you can go through the pictures, and a lot of colleagues who are effectively contributing to this.
So I hear there's a new project on the eye. Can
Yes.
you tell us more about that?
I would love to. Did we screw up? So we can skip these slides and go to the eyeball. Exactly. Go back a little bit. Back. Yeah. Here. Okay. Right. So this is Anne, and thank you for coming here. So a couple of years back, Anne was featured in the Wall Street Journal, and this is from the Union Tribune. What she has done is that she was able to revive the human eye from a dead patient for a few hours after their death. She was able to keep the eye alive. And this opens the opportunity, basically, to have the possibility of one day taking the eye and transplant it into a patient who is in need. If we're able to let the eye survive for the duration of transport and the duration of the surgery, then this would be possible. So one of my colleagues who was a patient of Anne introduced me to her, and we started discussing how can we measure and understand the electrical activity in the optic nerve a little bit better than existing equipment. Next slide. So this shows Anne in one of the discussions that we've done in my lab. So over the next a few months, we were brainstorming, and then go to the next slide, please. And one day, Anne calls me and tells me that there is a THEA program, and that's transplantation of the human eye allografts, a program that's started by ARPA-H. There's a press release about it today, and we are part of that project. So we partnered, and we were part of that project. What I didn't tell Anne at the time is that when we were discussing and brainstorming about the eye project, I was dating a very beautiful and smart woman in the Navy. And she's very inquisitive. And then I tell her a lot about the projects that I'm doing, and I told her that my dream is to go and do the transplant of the eye and connect the optic nerve. And a few months later, the RPH program was announced. So then I started thinking, beautiful and smart spy, taking all of our secrets to the government. But apparently, of course, Anne and her colleagues were thinking about this for several decades, and there are papers talking about eye transplants and connecting the optic nerve for a very long time. So it was just a pure coincidence. I really entertained the idea for a few days. In parallel with that, there were a few operations in the US where face transplants became possible. And this is one of the recent ones. It happened 1 year ago at NYU, where a patient was hurt from an electrical shock and had a very disfigured part of their face. They had a face transplant and also an eye. And the eye here had survived, it's perfused, there's blood flow, and the retina had survived. But the optic nerve is not connected, so there's no vision yet. So the goal of this new program is to be able to restore vision. And it's a very, very difficult problem. There are many parts. I think we are running out of time, so I'll not talk about the details, but basically the goal is to make this connection work. So where does my role comes in is to help make the electrical connections. This is the announcement that came today. Basically what we will do, can you go, stop here for a second. We have the LEDs that I showed you in the previous slide. We're going to implant tens of thousands of these LEDs on the surface of the retina and be able to map in the visual cortex how the retina is encoded in the visual cortex, also with the high density brain grids. One more slide, please. We're going also to record in the cross-section of the optic nerve so that we identify, for instance, where the macula, the highly sensitive region for our vision, is encoded in the optic nerve, so that we can tailor our devices and surgery later to make that connection for these particular nerves for vision. So we'll transition to animal and human work. This is the device that my lab will produce, where we'll use electric fields to guide axonal growth in order to make the connections. And then we'll assess the function if the junction has been formed electrically by stimulating and recording. So that's the story about the eye project.
Thank you so much. That's also interesting. Can you maybe tell us a little bit more about the company and how that translates directly to patients?
Yeah, those are the slides that we skipped. So basically in one of the events at UCSD, yeah, you have it there. Now forward.
There's nothing.
Yeah.
Oh, no.
So
This one.
yeah, this one. So we founded a company called CortiSci Incorporation. In short, it's CortiSci. And there was a seminar at UCSD. Sanjay was invited, and Sanjay Jha, who is a tech pioneer, he was an engineer at Qualcomm, and then rose in the ranks to become the CEO. And then he went to Motorola and Global Foundries. So during his talk, he mentioned about using technology for biological interfaces. And he talked about 4,000 sensors or so to aid in surgery. And I happened to be there, and I have the 4,000 sensors. So I told him, here it is, it's already happening here. So that started the conversation, and over the next 1.5 years, we started building the concept of the company and having people from different areas, technology. So this is the digital technology, neurosurgery here. I'm the interfaces, and then we have data science and the financial team. One more slide, please. And we have distinguished colleagues who are on our scientific advisory board covering neurosurgery and neurology and neuroscience. And our goal, basically, this is the operating room. And this is where the surgeon is operating on the head of the patient. You can see how much equipment there is between, in the operating room, between the surgeon and the electrophysiology team on this side. and though they communicate now verbally. So what the company will do is consolidate all of this equipment and make a wireless interface that can merge multiple modalities to inform the surgeon better to take their surgical decisions. And then we'll go toward an ambulatory monitoring and then go toward neuromodulation as the last phase. So this is the startup story.
That's
Hopefully
great.
the wireless will be better than the clicker.
Congratulations on that. And I just want to, at the end, maybe go back to Lebanon and ask what your thoughts on the best way we can help Lebanon advance. That's
Yes.
a broad question, I know.
Yes, and a tough one. You know, I think many generations didn't figure that out. But I think, yeah, I brought up actually the aspect about my upbringing in Schneller, because that's the foundational, right? So education is, of course, the foundational. If we are able to unify our curriculum for students so that they are all, learning and serving a single country, and if everybody, sings the Lebanese anthem, not only in the morning, but even when they ride in the car and before they sit on dinner, then we can instill this sense of citizenship within our upcoming generation. So this is a educational change. It's also part cultural. Other thing cultural, would be that every one of us do their best always, regardless of what's happening around them, and not to blame politicians for not setting up a good country for us. We can set that country. We have a responsibility, and if everyone does their job, and we collectively do their job, then it's the entire nation that's doing their job. Then it becomes a country that we would want to stay in and live in, and not go abroad in order to seek opportunities for our lives. So I think, we need an intellectual awakening. And I don't know how can we slide that in today's age into Lebanon. Maybe through education, maybe through seminars and programs. But I think, every one of us, in our own way, it could be very small, but it could be a contribution. Whatever you can do, even encouragement. I said my story, usually I don't talk about my upbringing, but I said it to inspire people who may feel that they may not have a chance because they come from a low-income or middle-income family. No, you can change that, and the world is limitless.
That's so inspiring. Thank you so much. It was my pleasure to chat with you,
Yeah.
Professor
Thank you
Shadi,
so
and
much.
thank you everyone for coming today.
Thank you.
Thank you.
So thank you again, Reem and Shadi, for this nice evening and getting